G'day viewers, in this episode we are concluding our derivation of a stable element-115 isotope. We present two possibilities for stable isotopes appearing in the top right hand corner of the screen. We predict that a stable isotope of element-115 exists with atomic weights of 258 or 296. We consider the 258 isotope to constitute a low probability of existence, whilst we consider the 296 isotope to constitute a high probability of existence. In other words, we feel as strongly as possible that either isotope of element 115 exists. However, on balance of probabilities, we believe it will be isotope 296. The manner in which we arrived at our forecast is displayed by the cartouche appearing on the left-hand side of the screen. It contains a Venn diagram which communicates the nuclear stability techniques we've utilised to date. The set appearing on the upper half of the cartouche was generated via nuclear scaling, whilst the set on the lower half of the cartouche was generated by constraining the construct to Potter geometry. Most importantly, the intersection of these two sets denotes the island of stability. The technique of nuclear scaling involves utilising the experimentally synthesised moscovium-290 isotope, which is unstable, as a frame of reference, and scaling the predicted atomic weights accordingly. In addition, in order to facilitate this method, the theoretical mass density value of 13.5 grams per centimetre cubed was applied. However, it should be understood that this theoretical mass density value, which was derived by Burkhard Frick in 2007, assumes nuclear stability. So it was never a perfect fit with isotope 290 to begin with, despite being the only official value that we could source. We consider it to be an official value because it originates from the University of Kassel in Germany. The technique of geometric constraining involves utilising Potter geometry to constrain the gravity A wave fundamental wavelength to the diameter of the waveguide, which acts as an antenna. This, of course, is predicated upon the assumption that Potter either derived his geometric values scientifically or obtained them directly from Bob Lazar. Either way, the technique of geometric constraining requires treating Potter's values as being exact solutions. Please continue watching this video all the way to the addendum on the last slide. It contains more information regarding the formulation of the cartouche. It should also be noted that our final two stable isotope positions represent a merger of fundamental particle physics, that is the EGM construct, nuclear physics and standard electromagnetics. Okay, I've bamboozled you enough, let's get into it.
In this frame we see two illustrations. On the left-hand side, we see the element-115 reactor and waveguide assembly as described by Potter. On the right-hand side, we see the element-115 fuel wedge manufacturing process as derived by Storti. In both illustrations, all dimensions are expressed in terms of the letter R. This means that, irrespective of the value of R, the entire solution scales proportionally. It also means that the ratio of the volume of the primary wedge to the volume of an uncut cone is the same for all values of R. Hence, this is termed the ideal volumetric ratio. Let's now have a look at what the ideal volumetric ratio buys us on a nuclear stability diagram. By enforcing the ideal volumetric ratio, whilst satisfying the Lazar primary wedge mass requirement of 223 grams, we're able to identify four potential element 115 isotope candidates. Three of them reside on the beach of the island of stability, indicated by the purple circle, whilst isotope 258 is lost at sea. However, just because it's lost at sea doesn't mean that it's an impossibility. It could just mean that it occupies a place where our knowledge of nuclear physics is incomplete. Let's not forget that prior to Edwin Hubble, standard astronomy thought that our Milky Way galaxy was the entire universe. Moreover, let's not forget that Albert Einstein, the man who bested Sir Isaac Newton, believed that the universe was static, that is, not expanding. We now know how ridiculous this idea was, and it came from Einstein no less. Anyway, the point I'm making is that scientific history is littered with bad ideas, and the idea of isotope 258, stability being impossible, may be one of them. So don't be too certain that it can't be stable just because an incomplete diagram suggests it. We've also included a polynomial of best fit appearing as the solid red line in the illustration. This is something we had to eyeball because we don't have the actual data points for a mathematical equation, but as you can see quite intuitively, our prediction of 180 and 181 neutrons hits the target perfectly. This is very encouraging. Here is a tabulated representation of our nuclear stability diagram based upon the ideal volumetric ratio. The key points appearing here are: number 1, the Lazar 223 gram primary wedge mass requirement solution sits well outside the island of stability as we saw on the previous slide. Number 2, all solutions satisfy Potter geometry precisely, that is, a waveguide diameter of 80 mm and a dome diameter of 280 mm. Number 3, no cylinder machining waste exists for any solution, that is, 100% material utilisation occurs. Number 4, 3 of these solutions do not obey Lazar's 223 gram requirement. Number 5, 3 of these solutions reside on the island of stability. And number 6, all solutions utilise exactly 16 discs. When we break away from the ideal volumetric ratio and allow it to vary, it's easier to satisfy the Lazar primary wedge mass requirement of 223 grams. However, this comes at a cost. The key points here are: number 1, no cylinder machining waste exists for any solution. That is, 100% material utilisation occurs because the height of the cone/cylinder equals 4 times the gravity A wave fundamental wavelength. Please refer to the manufacturing process diagram on slide 2 to refresh your memory of how this works. Number 2, only one solution satisfies Potter geometry precisely, but it sits well outside the island of stability. Number 3, all solutions satisfy Lazar's 223 gram primary wedge mass requirement. Number 4, 3 solutions reside on the island of stability. And number 5, all solutions utilise exactly 16 discs. Let's now have a look at what happens when we allow the number of discs to vary. The thickness of each disc is important because it's constrained to 1/4 of the gravity A wave fundamental wavelength. This means that the number of discs determines the height of the cone/cylinder. Thus, the height to gravity A wave fundamental wavelength ratio determines the proportion of element 115 cylinder material which will be machined away, thereby constituting waste. The ideal height to wavelength ratio is exactly 4. When this is achieved, 100% material utilisation occurs and no element 115 material is wasted. When this ratio is greater than 4, some element 115 material is eventually wasted, no matter how much of the milled material is collected, smelted and reprocessed. This table shows that approximately 4% of element 115 material will be wasted per cone/cylinder for any of these solutions residing on the beach of the island of stability. The key points presented on this table are: number 1, 3 solutions reside on the island of stability. Number 2, all solutions possess the same gravity A wave fundamental frequency. Number 3, all solutions possess the same gravity A wave fundamental wavelength. Number 4, all solutions satisfy Lazar's 223 gram primary wedge mass requirement. Number 5, all solutions satisfy Potter geometry precisely. Number 6, the height of the cone/cylinder does not equal 4 times the gravity A wave fundamental wavelength for solutions on the island of stability. Hence, cylinder machining waste exists for all island of stability solutions. Number 7, only one solution utilises exactly 16 discs. That is, only one solution produces 0 cylinder machining waste. So, why is this last point important? It's important because a stable isotope of element 115 is more precious than diamonds. It is literally priceless if it possesses the gravitational properties claimed by Bob Lazar. Hence, not a single atom of element 115 can afford to be lost. Let's now summarise what we've learned. Our investigation supports the conclusions derived in previous episodes. That is, a stable isotope of element 115 is likely to exist on the beach of the island of stability, somewhere between 295 and 301. Moreover, based upon the principle of utilisation, isotope 296 is the most suitable because only approximately 0.06% of element 115 material is lost across a batch manufacturing size of 25 cylinders. Hence, we're left with two possible candidate solutions, as appears in the table. Isotope 258 cannot be conclusively excluded from possibility because it might occupy a place where our knowledge of nuclear physics is incomplete. Therefore, isotope 258 denotes the ideal solution. In actuality, it represents the clever solution because the machining process does not produce any waste material. However, it sits outside our current understanding of physics. Isotope 296 denotes a theoretical scientific solution residing on the island of stability, but produces waste material resulting from the machining process. We stress that the contents of this episode are purely conjecture. The conclusions presented may be incorrect, so viewer discretion is advised. For those viewers with enough endurance, we'll walk you through the manner in which we arrived at our forecast. If you've been a regular viewer of this channel, you'll be familiar with the island of stability. We'll begin by graphing the isotope possibilities we have proposed across 3 episodes, that is, across episode 58, episode 60 and this episode. As usual, the purple circle denotes the island of stability. Appearing in the bottom right hand corner of the screen, you will see a cartouche containing a Venn diagram. This diagram communicates the nuclear stability techniques we've utilised to date. The set on the left hand side was generated via nuclear scaling, whilst the set on the right hand side was generated by constraining the construct to Potter geometry. Most importantly, the intersection of these two sets denotes the island of stability. The technique of nuclear scaling involves utilising the experimentally synthesised Moscovium-290 isotope, which is unstable, as a frame of reference, and scaling the predicted atomic weights accordingly. In addition, in order to facilitate this method, the theoretical mass density value of 13.5 grams per centimetre cubed was applied. However, it should be understood that this theoretical mass density value, which was derived by Burkhard Frick in 2007, assumes nuclear stability, so it was never a perfect fit with isotope 290 to begin with, despite being the only official value that we could source. We consider it to be an official value because it originates from the University of Kassel in Germany. The technique of geometric constraining involves utilising Potter geometry to constrain the gravity A wave fundamental wavelength to the diameter of the waveguide, which acts as an antenna. This, of course, is predicated upon the assumption that Potter either derived his geometric values scientifically or obtained them directly from Bob Lazar. Either way, the technique of geometric constraining requires treating Potter's values as being exact solutions. Consequently, we predict 2 potential stable isotopes of element 115 exist, that is, isotope 258 and 296. We consider the 258 isotope to constitute a low probability of existence, whilst we consider the 296 isotope to constitute a high probability of existence. It should also be noted that our final 2 stable isotope positions represent a merger of fundamental particle physics, that is, the EGM construct, nuclear physics, and standard electromagnetics.